everybody. My name is Dulce Villarreal, and we are here in Librería de Satoshi, or Library of Satoshi. It's a learning hub for Bitcoin and Lightning, and this is the Mastering Bitcoin seminar. We are already in the half of the book, and we are so happy to have Darius. Darius is also a Bitcoiner, passionate about Bitcoin since few years, and we are gonna cover some Bitcoin transactions, information, and learning. And feel free to ask in the chat. And this will be in YouTube. Hopefully, you will see this video in YouTube. And welcome, Darius. If you want to do a quick intro, and I'd let you the floor.
Cool. Thank you, Dulce. Yeah, my name's Darius. I moved to the US in 2014 to do my PhD in neuroscience. And yeah, during that time, I fell down the Bitcoin rabbit hole since like 2017. And yeah, so I had like a non-CS background, but just gradually learned more and more. And so when I graduated, I joined a small startup called Bolt Labs, and we were working on a layer 2 protocol, very similar to the Lightning Network, but with some sort of added privacy features. And also during that time as well, I started contributing just a little bit to Bitcoin Core, mainly on the Python testing framework. And in January, I moved to BitGo, where I was working on the Bitcoin team as a software engineer. And yeah, when the price of Bitcoin went down a lot in July, then I was left from BitGo. It's kind of confidential, but anyway. Yeah, and then since then, I've been working with Chaincode and putting together like educational content for developers to understand how transactions are created and signed, with sort of examples in Python to go through like each byte of a transaction and what it does, and all the different types of transaction types as well. So I've started working on it. I have like one notebook so far that goes through pay to pub key hash, kind of from start to finish. And then the idea is I'll make like a series of notebooks. One will be like, pay to witness pub key hash, one for multi-sig transactions, and time locks, and different sig hashes, and all these variations that you can do with Bitcoin transactions. And I think what's nice about it is right now, if you want to understand how like a Bitcoin transaction is created and signed, there's like a few good books like the Programming Bitcoin and Mastering Bitcoin, but sometimes it's a bit tricky to follow from start to finish how it works. And the nice thing about these notebooks that I'm sort of going to go through is that we can start up like a Bitcoin D in the background, and when we create these transactions, line by line, we can run it through Bitcoin D, and it can tell us, if the transaction was valid or not. And doing that helps you discover a lot of edge cases as well, and also gives you some appreciation for transactions which are valid by the consensus rules, but might be non-standard. And so there's like a whole category of these non-standard transactions, which are basically very difficult, almost impossible to broadcast. So yeah, that's basically what I'm doing now. So I thought maybe because this is so like related to the content for this week of what you're studying, I thought maybe I could go through this, and it's a kind of win-win, because I think this might be useful for all of you who are interested in how transactions work, and also it's useful for me to get any feedback, or if you have questions. And I think there's basically like a complete overlap between any questions you'd have about this and stuff that was in the book.
Thank you so much.
Does that
Yes,
sound good?
and most of them, most of the people who are doing the seminar, they have already Bitcoin D in testing,
Nice.
and then they can follow you and continue the exercise offline too.
Yeah, great. There's only like a couple of things you would need to install to run this locally, like this Jupyter notebook and just like very few libraries at the top. So yeah, the idea is, let me see, so I have the GitHub repo for this. Maybe I'll drop the link in the chat. So right now it's just this, but basically there's one for addresses, one for hash functions. So in Bitcoin, you know, there's most people know about this SHA-256, but so yeah, you know, we have some example of, you know, importing from this library. And, sorry?
Sorry,
Okay.
somebody didn't mute itself.
Yeah, no worries. Yeah, and then maybe some questions at the end as well, like, you know, given this public key, which is the public key hash, and right now, you know, I have these answers as well. So there's one for like the hash functions, another one for addresses I'm putting together. So so basically you turning a private key into a public key, and then turning the public key into an address, like a pub key hash, yeah, like a base 58, for example. So yeah, things like that. And then this one is for creating a pay to pub key hash transaction. So all right, so I'll just go through what this does. Basically, all of this is just doing some like command line arguments to just start up Bitcoin D, remove any old data so that we have a new blockchain, starting up Bitcoin D. I think maybe I'll just go through this very quickly and then we can do questions. So in this first step, we'll create a pay to pub key hash address. I'm guessing most of you know what pay to pub key hash means, but in any case, so here we just make some, reg test is just like your own local blockchain that starts on block 0. And so the first thing that we're doing here is we're starting Bitcoin D in reg test because we have this reg test flag. And then we create a wallet, generate an address, and then we mine 101 blocks using generate to address. We do 101 blocks so that we can spend the block reward from the first block. So yeah, with Bitcoin, the block reward has to be 100 blocks old until you can spend from it. So that's what we do here. One thing I'll do actually is I can restart and clear all the outputs. So now you can see that we can run it like in real time. This takes a few seconds just to start up Bitcoin D. And then at the end, in a couple of seconds, we should have the new instance of Bitcoin D in reg test mode running. While that is happening. So yeah, we start off with a private key, and so these functions are defined in the address section, but basically this is obviously not a very safe private key, but we'll convert this into a public key, and then we'll convert it into a pay to pub key hash address. Then we'll use this Bitcoin D, Bitcoin CLI command send to address to send it to this address. And okay, so this ran, so we can run this now. So yeah, for this private key, this is the address that we're going to use. So we'll send that address using this command. And the thing that we get here is the transaction ID. So now this transaction ID has the UTXO that we can spend from. And here we can use these other Bitcoin CLI commands, get raw transaction with the transaction ID, and decode raw transaction and print the output. So, oh, one thing actually, I looked at mastering Bitcoin again recently is I think that some of the figures in mastering Bitcoin are a little bit outdated because it doesn't have these SegWit fields. But anyway, this is the output. Maybe you recognize it from the chapter if you haven't done this manually yourself. So yeah, we have the transaction ID, and now we have these two outputs, and we can see this output is the one that we're going to spend from now. This was the address that we put in. So here we just want to find which output is ours, because we have one output here, and then we have a change output here for the rest of the block reward. So, okay, yeah, the first thing that you do when you want to send Bitcoin to an address, let's say this is the address that we want to send to. Yeah. So yeah, okay, maybe we can make this a bit more interactive. So what does this base 58 address actually encode? Does anyone know? Want to try and answer?
Chicos, pueden participar en español if you want, and we can translate.
Sorry. What was that?
Yeah, I said like if they want, they can speak in Spanish, and
Okay.
I can translate.
Okay.
Can you repeat the question? Can you say again the question?
Yeah, the question was so normally, so these base 58 addresses. The question I was asking was what information is actually like in this address for like a pay to pub key hash address. Yeah, so it's kind of, so the 111, that was the private key. So it's the, when we turn this into a public key, and then we hash the public key, and that's what ends up getting encoded in the address. So the address is the hash of the public key. Yeah, so I'll just run this part. So this address, when we decode it from base 58, base 58 is basically a way of turning this kind of hex values into a more compact and more, I guess, human readable, but not really, format, so that we can transfer these to each other. Yeah, okay, there's a bit more we could talk about with addresses, but I think we'll just try and keep this about transactions. So the pub key hash that we get from this address, the address, so we can refer to here. So here, this was the address that we sent it to. This address, what it really ends up converting to is this hex. This is a serialized version. This is the version, the sort of more human readable version. So pay to pub key hash means that the output has this locking script. So it's this op dupe, op hash 160. This is the public key hash, equal verify and check sig. And that means in order to spend from this, we need to provide the pub key, so that when you do this op hash, it will be equal to this pub key hash. And then you provide the signature, and that's what op check sig will verify. Yeah. So this hash, when we do op equal verify, is to check that the pub key that you put in to, like, in the script sig when you spend from it, it'll duplicate the public key so that there's 2 on the stack. One of the public keys will be hashed with hash 160. Then we put this one on the stack, and op equal verify will check that those 2 values are the same. Okay. Cool. And yeah, we're going through this a little bit quickly, but the main thing is I just want to communicate like what this does, so that hopefully you can go through this sometime. And also if you have questions, and then we can get to questions that you have. Yeah, this is like the matrix, exactly. This is really like, going down to each individual byte of a transaction. So yeah, you'll be, if you understand everything in the script, then I think you'll be pretty, you have a pretty deep understanding. Yeah, good question about testnet or regtest. So testnet and regtest are actually the same. So so this is the other notebook for addresses. Maybe I can make this a bit bigger. So for Bitcoin addresses, this is the function I was using in the other notebook, but here we put in pub key. This is a compressed pub key. That's the way we normally show pub keys. So we do this hash 160 to get the pub key hash. And if it's regtest or testnet, we have this prefix, or for mainnet, we have this prefix. So basically, regtest and testnet use the same address format. For mainnet, it has a different prefix, and this is to stop you from sending testnet bitcoins to mainnet. Yeah, so this prefix doesn't come up in the actual blockchain transaction. This is just for wallet developers or software to help users not make mistakes when they're transferring bitcoins. And actually, other Bitcoin forks like Litecoin, for example, they use like a different prefix, and that's to prevent you from sending Bitcoin to a Litecoin address and getting mixed up. Okay,
Perdón, Dulce, una pregunta, ¿puedo interrumpir?
Yes, of course. Sí, adelante.
Nada más para ver si los chicos están aprendiendo antes de que avance más, para que si llega a haber una duda en lo que ya está explicando Darius, la pueden hacer en español la pregunta, porque aquí Fiersec nos está diciendo que no está comprendiendo mucho, y antes de que avance,
dije
para que no
sí
se vuelva
comprendo. Lo que no entiendo es por qué.
¿Por qué qué?
Le estoy entendiendo, me sorprende a mí mismo saber que le entiendo.
Okay. They say, Darius, that
ya.
now they understand after
¿Qué
the
más?
explanation.
Muy bien.
Bueno.
Bueno. Azor has a question.
Yeah. Yeah. So, if you're writing a functional test for software, you'd write it very differently, but it kind of is, because when we go through, it will broadcast the transaction on regtest, and you can see that it works. So it's kind of like a test. Yeah. You could write a similar script as a way to test your software. Obviously we're not actually testing anything. This is just the script itself, if that makes sense. But yeah, the nice thing about having this go through Bitcoin D is that we can run the signature verification and stuff and know that it works. Yeah, Azor, did you want to say something as well?
Azor, do you want to say something?
Hola Dulce, hi Darius. Chicos, lo que Darius está explicando acá es básicamente cómo se arma un text funcional sobre una transacción en Bitcoin. Okay. Thank you, Darius.
Thank you. Okay, so So when we want to create the transaction, so okay, so this receiver address, we need to convert it into this script pub key. So yeah, this is just some Python code to convert this string into a hex, into bytes. In general, in this Python script, we work with bytes with everything. So yeah, basically we want to convert this address into this hex because yeah, the only thing that is actually in the serialized final transaction is this hex. You know, this hex. Yeah, so that's what we do here. This is for the receiver's output, and we also want to make a change output. So here we just make another private key for the change private key. So we just change this to a pub key, and then we have this is the locking script for the second output that we're going to create. And the other thing we need to define is the value of the outputs. So that's what we do here. Just as in Bitcoin, and we convert to Satoshis and turn it into an integer. So now we have all the information to create our transaction. So now the next thing that we do is we'll create an unsigned transaction, and then we'll sign it. So some of these fields hopefully maybe look familiar to you all. So we have this version field. This version field is 4 bytes, and the first version of Bitcoin transactions is version 1, but now most people use version 2. Version 2 just means that we might use these relative time locks. This BIP68 allows you to have a transaction where you say you can only broadcast this transaction if the input is more than 100 blocks old or something. So this is, yeah, we use these time locks a lot for like Lightning and things like that. And one thing to note as well is if you notice, this is version 2, but the number that we have here, or in bytes, is 020000 instead of like, it's not, we don't have it like this instead, even though this makes more sense to us, but it's because this is in little endian, which means all the bytes are reversed order to how you normally read it. It's a little bit confusing how this endianness works, but that's at least that's why it's like that. So
Darius, can you explain in simple English what is endiness, or say it again?
Yeah. So with it's to do with how the computers store bytes. With little endian, it means that it starts with the least significant byte and then reads the more and more significant byte. So if let's say we have a number like 123, this is like 123. The 1 is the most significant digit, and normally we read it from left to right. Like 1 means 100, 2 is 2 times 10, 3 is 3 times 1, and this would kind of be like big endian, the way we read it, because we start with the most significant. But in Bitcoin, in a lot of places, it uses little endian, so this same number would be written as like 321. And one of the reasons, for using little endian is it might be a little bit faster for some computers, because if you're adding 2 numbers together, let's say we want to do 123 plus 111, the way you do it is you start off with these little numbers first. You do 1 plus 3, and then that's 4, 2 plus 1, and the reason you do that is because if you have something like this, you want to do 9 plus 4 is 13, so you put the 3 and then you carry the 1. So just the way that computers were built, often they start with the smallest value first and then go to the largest. So that's what little endian means, basically, is you have it in reverse order. It's a little bit confusing why. It took me some
Yeah.
time to figure out, but
Thank you, Darius.
that's basically what it means. Yeah. And the reason for 02 is because 1 byte is 2 hex values. So, yeah. Okay, so with transactions, there's basically 4 fields for transactions. There's the version, inputs, outputs, and lock time. So now we go through manually and we'll set each of these. So here's the version. For inputs, we start off with the number of inputs, and we just have 1 input. So we do have 1 and convert it to bytes. Then for each input, we need the UTXO. So that's the transaction ID. And here, this transaction ID to spend is, we just save this from earlier when we did this send to address. We just save it here. So it's basically this value. And yeah, this is to convert it to little endian, but we can just sort of ignore that for now if you're not familiar with Python. And the index is which output. So the outputs have indexes, and our index, I think, was the first one. But yeah, basically these two describe which output you're spending from, which UTXO. So when we create the unsigned transaction, because we don't have any signature, we just put in these empty bytes. So we just put in 0. It means that our signature has a length of 0, kind of. And the sequence is, this is used for these time locks. We're not using any time locks, so we just put in the maximum value, which is just FFFFF. And with this value, it basically ignores the sequence field. So now we can put these together for our inputs. So we have the count, the previous transaction ID and index, empty signature, and the sequence. And now we do the same thing for the outputs. For the outputs, the number of outputs is 2. The value of the first output was, we defined it earlier. Here we're just converting it into bytes, into an 8-byte value. So do that. Yeah. So create war transaction. We'll do this under the hood. Yeah. So yeah, we have the transaction outputs, and then the lock time, we're not doing any time lock, so we just set this to 0. And this will be the unsigned transaction. I need to run some of these other fields. Yeah. The time lock will encode the block height as a hex value, and that block height is when the transaction becomes valid. Yeah, so now here this is the unsigned transaction. So you'd be able to pass this into Bitcoin D, and then put in your private key and then sign it. And so this unsigned transaction, we can also use Bitcoin D to decode raw transaction. So here we have this, this transaction ID is going to change when we put the signature in. And you can see here this script sig is empty. This is where the signature would be. But yeah, then we have our 2 outputs. These are the values we defined above. And these, if you sort of recognize, these are the script pub keys that we set, when we decoded. So here we had the receiver address, the person we're sending Bitcoins to, this MKX, blah, blah, blah. We decode this. We sort of take out the pub key hash and we turn it into this script pub key. So 76A914. These are the opcodes for like opdupe, op hash 160, and equal verify. So that value is now over here. This is our output. And with Bitcoin D, to make it more user-friendly, it converts this back into an address so that you can compare and see, okay, this is the right output. It's going to the right place. So, okay, so this is the transaction, but it's not signed yet. So when we want to sign it, we have to replace the field that was empty, the script sig, and here we put in the script pub key. So the script pub key is this one. We basically have to put in the script pub key of the transaction we're spending from. So from the input. So this is our new script pub key. We put that where our empty signature was. And this is just part of the signing step. So when we do that in our inputs, then this is the transaction that we're going to sign. So these bytes are what get signed. So the one thing we do before we sign it is we add this sig hash flag. This sig flash just specifies which parts of the transaction we're going to sign. So 0, 1 corresponds to sig hash all. It means that we sign over the whole transaction. And what that means is if any part of the transaction changes, then the signature will become invalid. And there's other types of signatures you can do to say, you only sign the inputs, or you only sign the outputs, or you only sign one input. And it's not, people don't really use it much, but what you can do with these different signatures is you can create a signature that says, you can use this input in any other sort of transaction, as long as it spends to this output. And that allows you to do things like create these bigger transactions, like coin join transactions and things like that, where you want to create a transaction with lots of inputs in a sort of collaborative way. And that way, each person can sign their own input if they want to. But that would be a whole section just for sig hash flags. Here we're doing 0, 1, which means all the inputs and all the outputs get signed, so nothing can change, basically. So we add this sig hash flag to this unsigned transaction. Then we do this hash 256. It's basically the SHA-256. We do it twice. And now we get 32-byte sig hash. And these are just two functions we import from this ECDSA library to create the signature. When we have the signature, we add this sig hash flag to the end. And now this is our signature. So now that we have the signature, our script sig is our signature and the pub key. That's the sig script signed. Yeah. So there'll be another notebook for Taproot transactions, and yeah, exactly. Instead of a ECDSA signature, it'll be a Schnorr signature. And this whole process will be a little bit different for Taproot transactions as well. But yeah, exactly. So yeah, the nice thing about this is you can really see the difference between these different types of transactions, which steps are different, because it is a bit confusing. So, okay, yeah, so we do all of this. Hang on, I need to run this section before. Great, and now we just, we put this signature inside the script, sig script. We put the sig script inside the transaction in the inputs, and now we have a signed transaction. So now we have a signed transaction, and we can do this Bitcoin CLI send for transaction, and now we get the transaction output. And yeah, we can look at the decoded version, and now everything is the same as before, but we have our signature in this serialized form here, and that's what makes it a valid Bitcoin transaction. Yeah, and then at the end, just some quizzes, and then the exercise that you can do is to spend another transaction from the change output, and you just fill in all the fields and then sign it, and then it should work as well. Yeah, so maybe we can either questions about this or just questions about the chapter. Hopefully I can answer any questions you have.
Yeah. First of all, I just want to say thank you so much, because I think in many years that I've been in the space, I didn't see something as kind of bit by bit or like piece by piece. I think you did an extraordinary work breaking in small pieces. At least I talk for me. I am mind blowing. Thank you so much, Darius. Like it is really good to see piece by piece, kind of what blockchain people say, block by block.
Yeah, thank you.
And
there are some there's some
Go
very
ahead.
nice blog posts, but they're just like one type of transaction. So what I want to do is have this for each type of transaction, witness, SegWit transactions, multi-sig, multiple inputs, different sig hash, time locks, so that everything becomes easy to understand.
And also multi-signature wallets to later understand Lightning, I guess, right?
Sorry, what about Lightning?
Yeah, like understand how works multi-signature transactions to later also, I guess, understand channels in Lightning Network.
Yeah, exactly. Okay,
Yeah.
we have some questions.
Yeah, let's check.
I'll just read. Okay, so Luigi saying regarding the UTXO, how do the scripts with flow control and complex scripts work? Yeah, good question. So yeah, this is pay to pub key hash. So there's no scripts here. But let me think. Yeah, there's nothing here that would be that useful. But basically, so when we make this script pub key, here we have the pub key hash, right? And here this is the pub key. This is just a hash of the pub key. For the script pub key, for the pay to script hash, this will be a hash of the script, and the script will be the locking script, and in there you can define these different flows. You can have like a if statements. So there's like a op if, and so if the script has evaluated to, I think, like if there's a 1 on the stack, then it will go through one branch, otherwise it goes through another branch. Yeah, it's basically like a very simple programming language. It's a little bit complex. Let's see this. So there's this website, this Bitcoin ID. I think you can see this. Okay, yeah, so this is handy. So this is an example of like a script using just some maths. And you can so here you can step through, for example, if we do 4, adds a 4 to the stack, op dupe or duplicate it to make 2 4s. Op add them together to make 8, and then we add 8. We can see if they're equal. So yeah, there's like a commands with like op if. This Bitcoin script is too kind of weird to try and program something or like freestyled, but basically usually it's something like there'll be some, like for Lightning, for example, there's like some public key, a bunch of numbers, and it'll be like op hash 160, and if the input hashes and is the same as this, then it will do one thing, and I think you'd have like op else, and if it's false, then it does some other path. And basically, yeah, thanks for the URL. And basically, at the end, the stack can take, you know, either path, and as long as you end up with a 1 on the stack, then it's a valid transaction. Hopefully that makes sense. Yeah. Cool. Okay, so different sig hash. Yeah. There's some so yeah, the sig hash flags, let me see. So the way it works, I don't remember off the top of my head all the different sig hash flags, but I think there's like, yeah, so we put it in here. So when we put the sig hash flag in here, this is basically telling the nodes when they receive this transaction, you know, like what are you expecting to be signed by the transaction. So there's like, you can say that you're only going to include your input, or you're only going to include one output, or you're going to put in all the outputs. So basically, the way it would work is when we sign this here, we have this serialized thing, transaction to sign, and that's what we create up here. And here we just use the same variables that we defined above, but let's say, I think it's like sig hash anyone can pay. I think what that does is that signs over, I forget actually if it's, I think that's like, it only signs your transaction, your input. But basically, the transactions that you want to include are the transactions that you include in this hex. So for example, I forget which sig hash flag it is, but if you only want to sign one of the outputs, then
give me a second, Darius, to mute
sure.
somebody. Yeah.
Okay.
Thank you. Sorry, Darius.
So, yeah, no problem. So here, like in this in these transaction outs, we have these two outputs here. I have to remember like what it is, but I think if you only want to sign your own, if you only want to sign one output, it's something like, you know, this is just zeros here, and this transaction outs is like, this is like zeros, something like that. And then you create the signature, you know, with those in the outputs. And then when you have the signature, then you can go back and add some other outputs to these transactions, and the signature should still be valid. I think there's like 3 or 4 different types of sig hash flags to allow you to create signatures that sign just isolated parts of the transaction. And usually they're generally useful for cases where you have like lots of different inputs, and that way each signature can have a different sig hash flag on it, and that allows whoever signed it to kind of basically put in some condition to say, you know, someone else can add an input or can add an output as long as the parts I signed over are still valid. Okay.
Thank you. There is another question that said,
this expense conditions, at least the English one, or you can translate the Spanish one.
Okay, it's a. Give me. Yeah, Azur has a question. The next question is Azur question, and say, are you using expenses or expense condition to test the scripts?
I'm not sure what expense condition is, but I think you mean like a failing condition, maybe?
Azor?
Yes, Darius. And conditions can. Or spend condition.
Okay, yeah. So, yeah, for example, like, let's say in, yeah, I mean, if I change, okay, so, let's say, okay, I'm just going to run the script again, but instead of doing send raw transaction, I'll just do test mempool accept. That way I can go back and change something in the transaction and test it twice. Just because I already sent the transaction, so I can't send it twice, but hang on. Oh, yeah, that's okay. Yeah, so we can change something in the transaction. Let's say in the signature. Sorry. Yeah, if I change this pub key hash part. Okay, so basically I ran through everything again, but here we say test mempool accept. It basically tests if the transaction is valid without broadcasting it. And here it's valid. That's why it gives us this allowed is true. If I let's say I just change this sig hash to 2. I'm not sure which one this corresponds to, but now we get a new signed transaction, and there's probably a 2 somewhere in here from what we just changed. Now if I try this, allowed is false, and it says mandatory script verify flag failed. Basically it says signature must be 0 for failed check sig operation. So yeah, I don't know if, and something that's kind of nice is we can change different parts of this to see how it would fail in different ways. So for example, like this transaction ID, well, let's just say this index I'll just comment out the actual version. Index to spend let's just say this is 3. So there's no third index on the input that we're spending from because there's only 2 outputs. Let me see. I think this was a string. I'll just run everything again. But yeah, but basically it's there's some failing conditions which means we know that it's actually working, if that's what you are asking.
Yeah, thank you, Darius. Let's see. There is another question from Luigi 1651 that say after the implementation of subt for signature management, how is the weight of transaction calculated and how does subt affect it?
Yeah, that's good question. So yeah, I guess it would have been handy if I had like a pay-to witness pub key hash example, but basically in the final sort of transaction, so we have this like version, transaction in, transaction out, log time. For witness transactions, we have like we have a witness field. There's two other small bytes in here as well, but basically this witness field would contain this this script sig. So it would be it's not real code, but it would be like this witness field would have this script sig, and here would just be like the empty script sig. So actually, when we had an unsigned transaction, it's basically like that. It's just empty. And the final transaction would have the script sig in this witness field. And with the witness field, there's this kind of SegWit discount. So usually we think of the fee in terms of like Satoshis per byte. And the bytes are, you know, each one of these is each like 2 hex values is 1 byte. But with the witness field, I think it's like divided by 4. So it means having 4 bytes in the witness field costs the same as 1 byte outside. And at least for pay-to witness pub key, the signature is like one of the biggest fields, the signature and the public key. And so when all of those go into the witness, it means you get like all of that is discounted. So that makes it cheaper. Oh yeah, sorry. And so the weight is like the newer way to measure the fee, and 1 byte is 4 weight units. So it's basically the equivalent. Everything outside is the number of bytes times 4 to get the weight units, but everything in the witness field is just 1 byte is 1 weight unit, and the fee is in terms of Satoshis per weight unit.
Yeah, I remember we were in Chain Code Lab seminar when March explained that kind of Bitcoin core developers are trying to do different things to make Bitcoin, let's say, to escalate Bitcoin or to improve the scalability of Bitcoin. And we know when fees are super high, there is not going to be a massive adoption. And they say they always trying to find ways to be easy to use Bitcoin for anyone. That's kind of what March explained in one seminar. And I think sometimes we think about Lightning that the only solution for scalability, but actually Bitcoin core developers are always looking for ways to make Bitcoin adoption bigger, maybe the mempool or the weight or second or third layer solutions. And I like to think like everybody is doing their own work to make Bitcoin adoption possible around the world.
Yeah.
Awesome. There is another
exactly.
2 questions.
Yeah, so the witness field is defined by default when you do create raw transaction. So Bitcoin D, when it's signing the transaction, it will know whether you're creating a SegWit transaction or not. And so if it's a SegWit transaction, then then in the output it gives you, it'll create this witness field and it'll put the signature in there. If you're creating like a non-SegWit, then it will do it like the other way. So yeah, but Bitcoin D, that sound surprised me. Yeah, it manages that for you. Yeah. How do you explain the white paper? Yeah, I don't know. You're probably as good as me, and for that, it's not easy.
Yeah, Luigi is one of our more humoristic members in the space.
Yeah, it's so hard, you know, especially like explaining the value of money and all these kind of things. You know,
Yeah,
if money if your Venmo or whatever works well, then why do you need Bitcoin? So I think there's also a few things like these hash functions, signatures are just you need to understand what a hash function does to appreciate the security. I think that's, but nobody really knows what a hash function is. There's a few things like that that are tricky to explain, but SegWit transactions, to see the difference. Yeah, you know, let's say I'm planning to work on it today. It's more than just it's a little bit more than just this. The differences aren't big, but yeah, it's too much time, too much pressure to do it now.
yeah,
But basically it's something a lot like this. The signature goes in the witness. One difference is you don't. Here we put this input script pub key. I think you don't need that. I think this is also just like that. I think maybe this is. I think maybe that's actually the biggest difference. It's something like, oh, and one other thing is this output also has like it's called like a marker and flag. These are basically like I think this is like something like this, and this flag is the like SegWit version. So I think the sort of what we call SegWit like version 1, I think it's 0, and maybe Taproot is version 1, something like that. But just for like pay to witness pubkey, it's like that. I think this is like 90% of the difference, but there's some other difference probably.
thank you, Darius. Also,
Yeah.
if you have other questions about the chapter 5, 6, 7, or in general about this section of the book, feel free to ask, and feel free to write in Spanish. I'm going to do my best to translate in English. Oh, go ahead, Entre Plantas y Ballenas.
Thank you, Dulce. I just wanted to ask if you could maybe make a rough explanation of how CoinJoin works.
Yeah. So usually with transactions, you know, we have these lists of inputs and outputs, right? We just put them all together here and put them all together here, and so you know, so one thing I'm not completely sure on is the protocol of how the signatures how it kind of goes back and forth. In general, you need like a coordinator to pair up like these inputs, but if that's what you're asking, I don't remember the details, but basically in terms of what the CoinJoin out transaction itself looks like is you'll have you know, a bunch of these outputs that'll have the same value, and these script pub keys will be different because, you know, maybe one belongs to you, one belongs to Dulce, one belongs to me, and then the inputs. This is just for one input, but yeah, we have like many inputs. I'm not sure if they take advantage of. I think they might use these sig hash flags so that everybody just signs their own input and 1 Bitcoin. And these inputs, so actually, yes, it's interesting. In the Bitcoin transactions, the input isn't specified anywhere in here, but it's the value of the, the output with this transaction ID and index. So, I mean, you could put in an input that has, let's say, a value of 2.5, and 2 of these outputs will belong to you, and there'll also be like a bunch of change outputs. Let's just say, that there's a bunch of these. So, not everyone is going to put in the exact value of one of these outputs. So the excess will be, this will be your output, my output, everyone's outputs. So these will, these make sure that you sort of keep most of your value, and there might be some like random fee amount so that it's not obvious whose change belongs to who, but then at least these outputs are kind of anonymized within the inputs that are provided. So, let's just say there's a bunch of inputs, and now you don't know, maybe this one was my input and this one is my output. But anybody who looks at the blockchain and looks at this transaction doesn't know if, this output is mine or this output is yours, if that makes sense.
So the input, just sorry if I'm taking too much time. The input is like signed by, I mean, if you have one address and you have one signature, you create, well, you have to sign it, your UTXO, and add it to the inputs, to the list of inputs, and then I have to add my UTXO as well with my signature. But who builds the transaction?
Yeah, that's a good question. So there's usually like I think there might be there might be multiple implementations of how these CoinJoin protocols work, but generally there's a coordinator, and the coordinator just matches up people who are like potentially good inputs for CoinJoin, and then I think there's kind of like, I think the coordinator puts together the unsigned transaction. So it would have all these inputs and outputs, but no signatures. So it would be like the unsigned transaction we created earlier. All of these script sigs are empty. And then that data, it sends round to the participants and gets them to sign their inputs. And then at the end, it has the fully signed transaction and it broadcasts it.
Okay, so the coordinator would have to be centralized.
Yeah, it's kind of centralized, but it's one of these things where it's trustless and anyone can be a coordinator, like using your Raspberry Pi kind of thing.
Oh, okay. Thank you. So
Yeah.
it's like connecting your node to a group of nodes, and
yeah. I
can send a
think like
transaction.
this Samurai wallet, and there's some other software you can run that it makes it easy to connect to a coordinator and participate in the CoinJoin. And I think the coordinator gets some like tiny fee for managing these CoinJoin transactions.
Great, thank you.
Yeah.
Great questions.
Yeah. So yeah, Luigi had a question about the node types. Yeah, I guess depends on how you define these node types, but generally speaking, there's like the full Bitcoin node that has all the blocks, all the UTXOs, and is running, the latest Bitcoin software. But then you can also have like a prune node where you validate everything, but you don't keep the historic blocks. And you can have these like simplified verification payment SPV nodes where you still verify things yourself, but you get the data from other nodes. Yeah, and there's maybe like some in between, but basically any node should at least verify the data, but the different types of nodes tend to be like how much of the blockchain data they store locally versus getting it from another node. Yeah, so can you practice the scripts in testnet? Yeah, exactly. So that's kind of one of these nice things. What you would need is you would need to have well, so actually you can use this script, for example, like you can use these functions. I mean, if you wanted, you could probably you could even use this address and you know what the private key is. So let's say on testnet, you create an address like this and you send some Bitcoin to this address. You can basically go through the script. You obviously have to change the amounts, and when we put in the transaction ID, where was it? So here we did like send to address, and this was the transaction, and this was the input that we used. We used this transaction ID and this index from here. If you get the transaction ID and the index, like your UTXO on testnet, and you sent it to an address that you generated using this public key, and you change the amounts to match up, then yeah, you can broadcast it on testnet with a hand-rolled Python transaction. And so this script specifically will only work for like pay to pub key hash, but in the next few days or maybe weeks, you know, I'll make one for pay to witness script hash, pay to witness pub key hash. The script hash ones will be maybe a bit tricky because you'll need to create. Actually, no, it'll be similar, but like with the multi-sig, you know, you'll create 2 of these private keys, then you'll have to create 2 signatures, but I'm going to make scripts for those. And yeah, yeah, I think it's nice to create a transaction from start to finish, line by line. You see every byte. Obviously, the hash functions and the signature uses some library because there's a, yeah, I think that's maybe excessive, but yeah, it should work on testnet. It would even work on mainnet as well. The only thing you would have to change is here when we create this address, here we say reg test, you just need to change this to mainnet, and then it would also work on mainnet as well.
Yeah, that would be actually really, really useful for those who have testnet. You can experiment it between you guys like a game. It will be fun actually.
Yeah. You can have a long chain of like passing the torch around.
Exactly. Yeah.
Yeah.
Okay. There is any other questions, or shall we start wrapping up? And just if somebody want to ask questions, feel free to write in Spanish or just say it in Spanish. Otherwise, we are gonna let Darius go because here is dinner time soon. Okay, it looks like we are getting to the end of this session. We want to say thank you to you, Darius. It was very, how to say, like, we learned a lot. I sometimes I don't find the words in English. See, but yeah, thank you so much. We will be checking the GitHub repository. There is a few developers joining for the next session, the next cohort for mastering Lightning, and we will be trying the Jupyter notebooks. Thank you so much for your time. We learned so much from you. I think now we can see how much you learn when you start working full-time in Bitcoin. And yeah, thank you, Darius. And see you in the next time. And Darius is gonna probably will be leading a seminar in the library. We don't decide yet if we are going to use like programming Bitcoin from Jimmy Song, or maybe we will use his brand new GitHub repository. But yeah, hopefully we can work in this in future seminars with Darius. And thank you so much, you all, for your effort and your work and the time you dedicate to Bitcoin and to share your knowledge about Bitcoin in the community. Thank you so much, and see you later, I guess.
Yeah. Thank you, Dulce, as well, for organizing this. Thank you, everyone. It's great. This is great, yeah. And feel free to message me, give me feedback if you have questions. It's always helpful for me as well.